In the previous lesson, we used Ohm's law to analyze the voltage and current divider circuits. The procedure we followed was to simplify the circuit into equivalent resistors in order to calculate the currents and voltages of the circuit. In this lesson, we will learn the first of two approaches that will allow us to analyze any circuit by following a list of steps. This method's name is mesh analysis. To better understand it, we need to learn the concepts of nodes and branches. In an electrical circuit, nodes are points where two or more components connect. In the following diagram, we can see them marked with red dots. This circuit has four nodes. The first one is the ground, which connects resistors 3, 4, and the voltage source. On the top, we can see the other three nodes connecting the other components. In the diagram, you can see lines next to each component. These green lines represent the branches. Branches are the paths that connect two nodes. For example, this voltage source is connecting this node to this node. Resistor 3 is connecting this node to this node. Resistor 4, this to this. And resistor 1 and resistor 2 connect these nodes respectively. The first step of the mesh analysis is to determine the loops. Loops are closed paths that we can follow. For example, if we start in this node, we can jump through this branch to this one, then to this one, and then we can go back to the initial node. We have another loop in this circuit. If we go from this one to this one, here, and we go back to the initial node. The difficulty of finding the loops will depend on how complex is your circuit. For some circuits, it's going to be very easy to detect them, like in this one. But as the circuit grows, it will be a little bit more challenging. And one recommendation is to redraw your circuit so you can easily find the loops. Another challenge that we can find when determining the loops is that sometimes some loops should not be considered. For example, here we have this loop 3. So we can start in this point, moving here, 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 and then going back. Why this is not a loop that we should consider? The reason is that every jump that we perform already belongs to a smaller loop. This one belongs to loop 1, loop 1, loop 2, and loop 2. So the loop 3 is completely covered by smaller loops. We need to be very careful in this situation because we may end up with incorrect equations. Once we have found all the loops in a circuit, the next step is creating one equation for every loop. For that, we have to assign a current for each loop. In this case, I have assigned a current name I1 for this loop and I2 for this one. The next step is to find the polarization of every component. In System Modeler, this step is very easy because every component already has markers describing which one is the positive and which one is the negative. We take the blue connector as positive and the white one as negative. Once every component is polarized, we need to write an equation for each loop. This equation is called the Kirchhoff voltage law, and it states that in a loop, the sum of all voltages across the components must be 0. For the loop 1, we will start here, and the first thing we can see is that we have a voltage source, and we are entering to the negative terminal and exiting to the positive. Therefore, we write the term as minus V1. Second step, we find the resistor 1. In this case, we enter through the positive one and exit through the negative. And we create the symbol VR1 to represent the voltage of resistor 1. The next in the loop is resistor 3. And we can see that we enter to the positive, exit to the negative. Therefore, we write its voltage as positive. I will repeat the process one more time. We start going through the loop. First, we find voltage 1. And we enter to the negative pin, therefore we write its voltage as negative. Resistor 1, we enter to the positive, and resistor 3, we enter to the positive as well, and we write those two terms as positive. With that, we have completed writing the equation for the first loop. We will continue with the second loop, and we are going to follow the same process. In this case, the current I2 enters into the resistor 3 through the negative. Therefore, we write the term as negative minus VR3. In the case of R2, it's positive, and resistor 4 is positive as well. What these two equations are telling us that for every loop, the sum of all the voltages is equals to 0. The next step is to replace the voltages of the resistors using Ohm's law. In the case of the resistor 1, the term VR1 can be expressed as the current I1, which is the one that is flowing into the resistor, times the value of the resistor 1. VR2, which is this one, it's the current I2 times R2. VR4, we have the current I2 times R4. The only special case is this one, is resistor 3, and we can see that we have two currents flowing through this resistor, I1 and I2. If you remember, I1 flows from the positive terminal to the negative, while I2 flows from the negative to the positive. So the effective current that is flowing through R3, it's I1 minus I2, and we multiply that by the value R3. After replacing all the voltages of the resistors, we end up with these two equations. And in these two equations, V1, which is the voltage of the source, it's a known variable. I1, it's an unknown, it's the current that we want to calculate. R1, it's known, currents are unknowns, all the resistor values are known. So we have two equations and two variables. And we need to solve these two equations in order to get the values for I1 and I2. We can easily solve those equations using the Wolfram language. Here I'm using the function solve that will produce a symbolic solution for these two equations. Here are the equations. They are provided as input. And the variables that we want to calculate are I1 and I2. After evaluating this command, here we can see the symbolic results. If we take these solutions and we replace the numeric values, we will obtain a numeric solution. In this case, the voltage 1, it was 10 volts, and all resistors were 1 kilo ohm. And this is the numeric result. The current 1, it's 0.006 amperes or 6 milliamperes, and the current I2, it's 2 milliamperes. Once we know the values for the currents, we can obtain any voltage in the circuit. For example, if we want to calculate VR1, the voltage in the resistor 1, we can take just the current 1 times the R1 value, which in this case will be 6 milliamperes, times 1 kilo ohm, and that gives us 6 volts. So resistor 1 is going to have 6 volts. We can do the same procedure if we want to know the voltages for the other resistors. Here is a summary of the steps necessary in order to perform the mesh analysis. First, we need to identify all the loops in the circuit. Once we have the loops, we have to assign a current for each loop, and we need to define the direction that we want the current to flow. After that, we define the polarization of each component. So we say which one is going to be the positive pin, which one is going to be the negative one. Then we write the equations for every loop using the Kirchhoff current law, which is basically a sum of all the voltages in the loop. After that, we rewrite all the voltage variables in terms of the currents using Ohm's law. And last, we solve the system of equations. There is one special case that we need to consider. This is the same circuit, but we have replaced the voltage source with a current source. In this case, the current source is part of the loop. Therefore, the current I1 it's a known variable. In this case, we don't need to write an equation for the loop, since we already know the value of I1, which in this case, the current I1 is equal to the constant current, which is also called I1 but uppercase. For the second loop, we do need to write the equation. And if we just replace the value of I1 with I uppercase 1 into this equation, we have to solve only a single variable. And this is the symbolic result. To summarize this lesson, we learned the mesh analysis, which is a systematic approach to solve a circuit. In this analysis, we write one equation per loop in the circuit. Once we have the equations, we solve for all the current variables in the circuit. And using the values of the currents, we can calculate all the voltages